So Jill Tarter holds the Bernard M. Oliver Chair for SETI Research at the SETI Institute in Mountain View, California, and serves as a member of the board of trustees for that institution. Tarter received her Bachelor of Engineering Physics degree with distinction from Cornell University, and her master's degree and a PhD in astronomy from the University of California in Berkeley. Yes. She spent the majority of her professional career attempting to answer the old human question, are we alone? By searching for evidence of technological civilizations beyond Earth. She served as project scientist for NASA's SETI program, the High Resolution Microwave Survey, and has conducted numerous observational programs at radio observatories worldwide. She is a fellow of AAAS, the California Academy of Sciences, and the Explorers Club. She was named one of the Time 100 most influential people in the world in 2004. And one of the Time's 25 in space in 2012. Received a TED Prize in 2009, 2 public service awards from NASA, multiple awards for communicating science to the public, and has been honored as a woman in technology. She was the 2014 Jansky Lecturer. In 2015, she became president of the California Academy of Sciences. She has a lot of things that she's known for. This is wow. So, how about we welcome Jill to the floor tonight?
Before we start, I'd like to just give you a little personal background. I got recruited to work on an early SETI project as I was leaving graduate school. And the recruiting document that I was exposed to was something called the Cyclops Report, an engineering design study written by Barney Oliver, head of HP Labs for decades, and John Billingham, the head of life sciences at NASA Ames. And I read through this document cover to cover. It was just amazing. And I understood that back there, in the middle of the 20th century, after millennia of asking the priests and the philosophers what we should believe about, is there life elsewhere? Is there anybody else out there? Suddenly, we finally had some tools that would allow scientists and engineers to begin to observe and try and answer this old question on the basis of what is, rather than on someone's belief system. And so I just was amazed that I was there with apparently the right tools at the right time to begin this scientific exploration. And so my whole career has been about trying to convert the verb to believe into the verb to explore. And so I've been incredibly privileged to spend a working career on this very old and important question and trying to systematically figure out, even if we can't find the answer now, what is it that we need to do to try and find the answer in the future? So it's been enormously rewarding for me. And so as I look forward to the 21st century, having been indoctrinated into SETI in the 20th century, I'm very much aware that in 2004, Craig Venter, Human DNA Project, and Daniel Cohen wrote a paper in which they claimed that whereas the 20th century had been the century of physics, right? Special and general relativity, quantum mechanics, Big Bang cosmology, dark matter, dark energy, the standard model of physics, et cetera, really very, very impactful and successful century. Their claim was that the 21st century was going to be the century of biology. And they were thinking about all of the genomics work and revolutions that they had started and seeded. And in this claim, I think they are unquestionably right. But I also think that that claim was just a little too timid. Because I think the most wonderful thing is that the 21st century will be the century of biology, not only on Earth, but beyond. I think this is the century where we're going to have some answers to part of this fundamental old question. And it's extraordinarily exciting. I wish I could live out the century. Don't think that's going to happen, but good things are going to happen. So when you talk about life beyond Earth, there are three ways that I think we will be able to justify that expanded statement. Life, biology on Earth and beyond. All right? We can imagine discovering it, either in situ in some bodies within our solar system, looking for biomarkers or maybe even evidence of extant life. Or we could think of finding it remotely, looking for biosignatures associated with bodies orbiting other stars. We could hope to communicate with it. Perhaps instead of biosignatures, we will actually be able to find technosignatures, evidence of technological civilizations elsewhere. Or, hello? Okay, I'm going to turn off my web browser, or my web connection. Sorry for this technical glitch, but I have to go turn off this, or we'll get that all night long. So we're back to this. All right. So deliberately searching, perhaps we will find technosignatures. That's SETI. That's what I work on. Or, in fact, we might serendipitously detect evidence of somebody else's technology by doing more and more astronomical observations of our universe. And finally, we might export it. All right? There's talk about humans to Mars, to the moon, back to the moon, asteroids. I am on the advisory board for the 100-year Starship study. Could we, a century from now, be capable of traveling to the stars? Don't know the answer to that. That's what we're working on. All right? And so I think that one of these three methodologies is pretty likely to provide positive results in the 21st century. And I look back over my career, which is long, and I'm astonished by actually two incredible game changers from the time that I was in graduate school until today. The first of those is the detection of extremophiles. These are forms of life. The majority of them are microscopic, but there's a whole lot of them that are macroscopic, that live in environments that are extreme, but they're extreme in terms of our frames of reference. These organisms are perfectly happy where they are. They're very well adjusted to living in ice, in boiling battery acid, in at huge pressures, without sunlight, at low pH, at high pH, with enormous radiation pressure. They occupy these niches everywhere that we as humans couldn't tolerate. And so when I was a student, we were still teaching that life required all of the things that we humans need. What a really skewed, incorrect point of view that is. And it took going and diving down to the bottom of the oceans where the Earth's mantle is breaking apart The crust is splitting, and there's this upwelling of magma and all of these nutrients at high pressures and high temperatures, and these amazing colonies of tube worms and other species. It took that to open our eyes and say, maybe we've been a little too parochial here in our definition of where life can exist. And so it's been an incredible explosion and a change of our point of view. And I think it's extraordinarily important that microbes are finally getting the respect they deserve. And I think it's also important because it's helped to change our point of view. It's helped to remove or cast aspersions on this ascent of man and humans being the pinnacle of evolution. I mean, we've had that point of view, but nature certainly doesn't, right? We are not the pinnacle of anything. We are the result of billions of years of evolutionary trial and error. And we are well suited to our environments, just as all of these extremophiles are extraordinarily well suited to theirs. And then the second game changer, from the time that I was a graduate student, when we had 9 planets in our solar system, is this whole idea of exoplanets, and eventually, we hope, exomoons, as yet not detected. So when I was a student, we were just transitioning out of one model of how stars formed and into the model that we have today, which seems to be very well supported by observational data. In the old model, which is that you got planets when 2 stars passed close to one another and pulled out material into a disk around their equators where planets could form. If that's the correct model for planetary formation, we wouldn't expect very many planets because stars don't get close enough to one another very often. Today we think that when stars form, the natural consequences of that are that they form with a disk of gas and dust around them from which planets can form. And the fantastic improvement in technologies over the past just 2 decades now allows us to make an incredible statement. Incredible by my standards for my graduate school, not knowing about any planets beyond our solar system. We can now say with statistical confidence that there are more planets than stars in the Milky Way. We know that. And it's amazing in one lifetime to go from we have no idea to we know this, right? And so, as a result, given extremophiles and exoplanets, there is probably more potentially habitable real estate out there than we have ever imagined. And that makes the question of life beyond Earth both timely and fertile. Okay, let's go find it. And so we're there. We're beginning to explore. Here we are on the surface of Mars. We're on the surface of another planet with a very credible and capable robotic laboratory, the Curiosity Science Lab. And Curiosity's job is not to find life on Mars, but to tell us whether the conditions, or at least the conditions that we think are necessary for life, in fact exist today on Mars or existed in the past. We've been thinking now for a while that early Mars was a lot wetter and warmer than it is today. But we haven't had the evidence. So first thing curiosity did was show us that indeed, with all of these deposits, these layers, that there was water. There was a lot of water on Mars, and it was there for a long time. And then much more recently, we know that in fact it's still there. There is a significant amount of water on Mars that is subsurface, and on the south-facing slopes in the summer, you get these recurrent slope linei, regions that are wetted downslope. And we know that the wetting agent is water. And so not only was there water on Mars, but there's still water there today. We know that Mars has lost a great deal of water relative to its early times. Mars basically is too low in mass to hang on to much atmosphere. And when the water molecules in the atmosphere, in the gas phase, are broken up by sunlight into hydrogen and oxygen, this photodissociation that happens all the time in our atmosphere too, Mars's gravity is too small to hold on to those little hydrogen atoms, and they escape. So Mars has lost a lot of its water, but we now know that some is still there. And so Mars is an obvious place for the next few decades for exploration, looking for evidence of extinct fossilized life, or even perhaps in some liquid aquifers subsurface today, extant life. And there are many programs that are being planned by NASA and ESA and perhaps the Japanese and Chinese space and Indian space agencies as well. And this exploration will go forward in the next decades. And if Mars turns out to have life, fossil life, extant life, we've got another question to ask. And that question is, are we Martians? Because early in the solar system, the terrestrial planets, Mercury, Venus, Earth, Mars, were all exchanging rocks. I mean, early on in the formation of the solar system, it was incredibly chaotic, and there were these rocky billiard games going on with things crashing into other things and things being exploded off surfaces. And so we know today that material was transferred from Mars to the Earth. How do we know that? It's because when we go down to the Antarctic in the spring as the snow begins to melt, and we find these melt pools with all these little black rocks in it, which are meteorites, and we look at the composition of some of those meteorites, we finally understood that a few of them are pieces of Mars or the Moon, and not just asteroids. So, if rocks could hop from Mars to the Earth early in the history of the solar system, might life have started on Mars, gotten itself warm and cozy inside a rock, and managed to survive the trip to Earth, and seeded life here? It is scientifically, in fact, to the best of our knowledge and calculations, a possibility. And so if we find life on Mars, we're going to have to very carefully analyze it to understand whether we and it are related. Are we Martians? Or, more astonishing, more exciting to me anyway, is the life on Mars evidence of a second genesis? Because if we find a second independent origin of life within this one solar system, we can be pretty confident that life is going to be ubiquitous every place out there that has habitable environments. Okay, so Mars and number 2, n equals 2 for life is a really big goal in the future. But what's beyond that? Well, there's the rest of the solar system. We've got the giant planets of Jupiter and Saturn. And around Jupiter, we have moons, ice-covered moons. Particularly the moon Europa, which is about the same size as our moon. But underneath that icy coating, we're pretty confident that there is not only liquid water, but maybe twice as much water as all of the Earth's oceans. And one of the potential origins of life theories is that life started at the bottom of the oceans on this planet, in the black smokers around those crustal vents. And so if life here started at the bottom of an ocean, what might have been going on for the past 4.5 billion years, the bottom of Europa's oceans? So we're really eager to probe that ocean environment. And it's not a simple trick. Think about boiling, melting, drilling through kilometers worth of ice to sample the liquid ocean beneath it. And doing so without introducing any microbial contaminants from life here. Because you would hate to find life somewhere else only to realize that you brought it with you. So that is a big challenge, and it's not going to happen the first time we go to Europa, but there are a number of scientists thinking about how to do exactly that. And then beyond Jupiter, there's Saturn, a very large moon, Titan. We know that Titan has liquid lakes on its surface. On the other hand, it's so cold that those lakes are not made of water, they're made of hydrocarbons, ethane. And we're wondering, wow, could this somehow talk about the early chemistry of origin of life on this planet? And so we'd love to revisit Titan in situ, get landers into those lakes, find out what's going on there. And then, big surprise, once the Cassini spacecraft started to orbit Titan, about 15 years ago now, it took some pictures of a tiny little moon called Enceladus. It's a pipsqueak. Who cares, right? Except that when we looked at those images in detail, this is what we saw. So the south pole of this tiny little moon called Enceladus has these cryovolcanoes erupting constantly. These plumes seem always to be there. And what are they made of? They're made of water and organics. This is the stuff that's coming from the liquid ocean under the ice of Enceladus. So now we have perhaps a free lunch. Instead of having to drill or melt or otherwise go through kilometers of ice, potentially we can just fly through this plume and pick up whatever is under the ice of Enceladus. So flybys and plume experiments are now being explored. Again, I say it's a free lunch. It's not going to be easy. It's just only easy in comparison with getting through kilometers worth of ice in a sterile manner. So we've got these bodies within our own solar system that potentially may show us a second genesis. And if it turns out that life on Earth is the only life in the solar system, or at least the only detectable life, well, the sun is not the only star in the sky, and we are looking for planets around other stars. Now, it's very hard to take a picture of a planet around even a nearby star, because planets are faint and stars are bright. If you want to compare the sun and the Earth in the optical, the brightness contrast is 10 to the 10th. 10 billion times. In the infrared, it's only 10 to the 8th. 100 million. Gets easier. We'll take every factor of 100 we can get. But occasionally, you get stars that are faint. You get planets that are young and therefore brighter because they're still condensing and giving off extra heat. And they're far from their star. So this is an image that was made a couple of months ago by Gemini, the GPI team, whom some of my colleagues are members. And this is the image of an exoplanet. It's here. It's 51 Eridani b, that blob there. This is a very young system, so that planet is still contracting and bright. And you can see the dashed circle. That is the orbit of Saturn, the size of the orbit of Saturn around the sun. So you can see this particular planet is very far from its star. We got lucky. So we actually, I've already made this statement that we know that there are more planets than stars in the Milky Way, and we're not finding them by taking pictures of them. We're finding them indirectly. All right? We're finding them by looking at the impact that a planet has on its star. So a planet in orbit around the star will tug its star towards you, and then when it's back here, it'll tug the star away from you. And with incredibly difficult measurements, you can see those small shifts in the stellar velocity by doing Doppler analysis of absorption lines from the star, this radial velocity wobble. We can see if the orbits are appropriately oriented. We can see sometimes when a star passes, when a planet passes in front of its star, it will cast a shadow, and the star's light will dim just a little bit during this transit. What do I mean by just a little bit? Okay, if Jupiter, big planet, passes in front of the sun, it dims the light by 1%. If the Earth passes in front of the sun and you're looking from a distance, it will dim the light by a part in 100,000. That's a hard measurement, but now we can do it from space. And then also occasionally you will get the appropriate alignment of a foreground star in front of a distant star, and you'll get gravitational lensing that brightens the distant star. And if there's a planet in orbit around the nearby star, you'll get a brief additional increase in the intensity of that background star. But again, this is gravitational lensing. It's been successful, but we never know which star and can't look back to find the planet again. But we nevertheless have been successful with these techniques. And just yesterday, all right, was the announcement with the radial velocity technique, the wobble velocity, by a team of Australian observers, that they had found around Wolf 1061 3 planetary systems. Now, what's so special about that? It's only 14 light years away. It is the closest planetary system that we've found. And one of those stars, the C component, one of those planets, is within what we call the habitable zone. It's at the right distance from its star to be not too hot, not too cold. If there's an atmosphere on that planet, it could have liquid water on its surface. And its mass is something like 4 times the mass of the Earth. So this is a super Earth. It's the kind of planet we don't have in our own solar system, but we are finding in great abundance around other stars. And we're incredibly curious about what a super Earth is like and whether in fact it represents a habitable environment. But when we try and find nearby stars that might have planets that we could study with the tools that we will be developing in the next few decades, we're going to be limited to M dwarfs, to small red stars, because about 75% of the stars in the sky are these little tiny dwarfs. You don't see them when you go up and look out at the sky at night. What you see is the big, bright O, A, B stars that are very far away. You can't see these little dwarf stars, but they are the most abundant. And we don't know whether they could be good hosts for life. We will find out, however. All right, so when we do these detections of extrasolar planets, we learn a few numbers. We can learn their size, we can learn their mass. When we can learn both for the same planet, we can get its density. We can guess about whether it's rocky or gaseous. But that's about all we can learn. If we want to learn about life, we've got to go the next generation of space-based technology. We have to be thinking about biosignatures. We have to be saying, all right, a planet shines because the light from the star passes through the planetary atmosphere, reflects off its surface, and passes back out and into our telescopes. Well, now, as that light is going through the atmosphere, if there are trace molecules or atoms in the atmosphere, they might absorb at particular frequencies, these sort of fingerprints of different atoms and molecules. And if we could observe the light reflected off a planet with sufficient precision for long enough, we might be able to tell what molecular constituencies are in the atmosphere. And so what will we compare it to? Well, we can't really get outside of the Earth at a large enough distance to do that experiment, but we can do the equivalent experiment by looking at the moon. So that very bright crescent, that's reflected sunlight. The gray part of the moon, which actually has a slight reddish tint, that's reflected earthshine. That's the light from the Earth bouncing off the moon and back into our telescopes. And since the moon has no atmosphere, what we're actually able to do is get a spectrum of the Earth's atmosphere, a spectrum that's averaged over the whole disk of the Earth, just like it would be from a distant planet. And we look at the telltale chemical composition of our atmosphere, and we see that it's quite different than the chemical composition of any other planetary atmosphere in our solar system. So water and carbon dioxide are common in other atmospheres, but oxygen and methane, which is not in this, it is, I'm sorry, it's down at the infrared 2.3 micron. The coexistence of oxygen and methane marks our atmosphere as very strange, very intriguing. Why is that? It's because if you go into the lab and you take oxygen gas and methane gas, and you put them together, you're going to get water and carbon dioxide. That's the equilibrium configuration. That's what those two gases like to turn into. But we still have detectable amounts of oxygen and methane in our atmosphere because we've got biology on the surface of the planet. And so all of our plants are photosynthesizing, and the small microbes on the surface of the ocean, photosynthesizing and putting oxygen into the atmosphere. And the methanogens in the rice paddies and in the guts of termites and bovine flatulence, cow fart, putting methane into the atmosphere. And don't laugh at the cow fart. It's a real large contributor to methane, which is a very strong greenhouse gas. It's a problem for global warming. But this disequilibrium chemistry is an indication that our planet has a biota on its surface. And this is the kind of thing we would like to look for in the signatures of the atmospheres of distant planets. Now, having said this nice story about oxygen and methane, I can't actually claim that that's a smoking gun. That if we saw that in another planetary atmosphere, we would know conclusively that there's biology on its surface. There isn't really a smoking gun for biosignatures. There are ways and unusual conditions in which you can produce most of these kinds of signatures abiotically, through geology, through chemistry. And over the lifetime of the Earth, our biosignature has changed profoundly. Until 2.4 billion years ago, we had lots of life on Earth. We're all methanogens. So we had a lot of methane, but there was no oxygen. It was only 2.4 billion years ago that blue-green algae, cyanobacteria, managed to discover this mechanism of photosynthesis that produced free oxygen. And after a while, in the oceans, enough of this oxygen was produced to have rusted all the iron in the ocean, and then it began to seep into the atmospheres. And we began to get an oxygen signature for the first time. If you ever want to get goosebumps, I urge you to go to Sharks Bay in Western Australia. It is one place on the planet where living stromatolites, things that look like Miss Muffet's tuffet of rock, looks like a rock, except that it's just layer upon layer upon layer of colonies of cyanobacteria. And only the outside layer is living. And these are underwater. And the Tourist Bureau at Sharks Bay has been kind enough to construct wooden walkways out among these. And you walk along that walkway and you look down, and there are all these little bubbles of oxygen coming up. And that's what was responsible for us as complex organisms to be alive today. That oxygen was necessary for a new metabolic pathway to lead to the complexity that is represented by us. Anyway, gives me goosebumps when I'm there. So, biosignatures we're working on. It's not going to be cut and dried. You're going to have to try and deduce a whole lot of context for these future observations that are going to have to be made from space. There are opportunities perhaps to detect space weather on these planets, to know whether it's cloudy, to see whether there's a glint off oceans. This is 20 to 30 years in the future, and it may not be crystal clear when we make announcements. They may have a lot of caveats, but this is a way that we may learn about life beyond Earth. And the future of this research in terms of imaging planets and looking for biosignatures, well, our first new major instrument will be the James Webb Space Telescope, which is supposed to launch in 2018. There are a few stars close enough that James Webb can make some detailed observations. They're mostly stars that have what we call hot Jupiters, planets as massive as Jupiter, but very close to their stars. This may lead us to a bit forward, but really it's going to be much more extraordinary imaging systems that we're going to need. Here's an indication of something that's called W1st AFTA. Really, really crazy name. W1st was a mission, and then the NSA found this old optical telescope that it was sort of spare, and it gave it to NASA and NASA decided to make a telescope out of it, and we've got this conjoined mission. But the interesting thing is that big petal shape in front of it. It's a star shade that flies many kilometers out in front of the telescope and tries to block out the bright star. Right? And then in the dim areas around that excluded starlight, you may be able to see planets. And eventually NASA is just now starting to talk about on its charts the large ultraviolet optical infrared telescope, right? They don't know what to call it yet. It's something that has a large enough aperture to perhaps be able to collect enough photons to do this chemical analysis of planetary atmospheres. So stay tuned. If you've got kids and grandkids, this is what's going to be their future. This is going to be what they're learning. And I'm excited by this. So, but I'm not willing to wait, right? I'm not going to be around for le voir or whatever it ends up being called. So I'm intrigued, instead of looking for biosignatures, let's look for technosignatures. Let's use the deliberate actions of any technological inhabitants to find these habitable worlds. So many of our technologies today on Earth are detectable at interstellar distances. Some of theirs may be as well. And that's what we're trying to find. And so at the moment, our search for technosignatures is ground-based, and it's being conducted in the optical and the radio portion of the spectrum. And these are smallish kinds of endeavors. They're not the large billion-dollar flagship missions that I've been talking to you about for finding the biosignatures. Okay, now, if we're looking for technosignatures, I'm going to claim that you're actually looking for deliberate signals, assuming that you're looking for electromagnetic signals, which has been our first guess. And why do I think you'll find deliberate signals rather than leakage? It's because these systems to transmit out there are built by engineers. And there's no engineer worth his or her salt that overbuilds a system, unless it's a bridge and you overbuild for safety. And some of us didn't get that right either. But if you're transmitting something, you're transmitting it to a particular audience, and you don't put any more power in the transmitter than is needed to satisfy your audience. And so leakage signals, at least our type of leakage, like radars and television signals, etc., are trying to illuminate the next county or over the horizon to see the bad Russians coming to invade us. They're not intended to illuminate at interstellar distances, so there's not a lot of power in these signals, and I think their leakage is going to be really hard to find. So I think about, all right, somebody out there is deliberately transmitting. What might that look like? And I think there are kind of two kinds of deliberate signals. There's signals that might appear to the receiver almost natural, or there are signals that might appear obviously engineered. So what's this almost natural? If you, as an extraterrestrial engineer, wanted to construct a signal that you could be sure that an emerging technology, that's what we are, folks. We're part of the youngest kids in the galaxy. We are a very young technology in a very old galaxy. If there are other technologies out there, they are older than we are. So you want to generate a signal, you can make sure that an emerging technology, which wakes up and starts to investigate its surrounding universe, you'll want them to stumble over it. So you'll make it look like something natural that they will catch in their surveys of their surroundings. So I've got a couple of examples of that. We've known about pulsars since the 1960s. Okay, can you turn on the... there. All right? That's a pulsar, a radio signal that's received with incredible precision, like a radio clock in the sky. All right? We have surveys looking for these things all across the sky. Huge, massive databases. Well, pulsars can sometimes change their frequency because there's a star quake and it changes the moment of inertia and the rate at which this pulsar rotates. But we've never found a pulsar that changes its frequency to another frequency, changes back again to the first frequency. All right, well, we're having a problem with the video. And then goes back to the second frequency. So we could detect those in our databases, in our pulsar surveys. And some graduate student or postdoc digging through these enormous databases would say, hey, what's going on? That's really weird. Frequency 1, frequency 2, frequency 1, frequency 2. That's really interesting. That might be a way that we could detect someone's technology. All right, here's another idea. We're doing transit observations. We're looking for the shadow that a planet gives to the stellar disk. Now, the IAU tells us that a planet, by definition, has to be round. So we would expect the shadow of a planet to be a circle. But suppose you decided, hey, those emerging technologies are going to be looking for other planets around other stars by this transit technique. Why don't we orbit something that isn't round? It's a triangle, it's a Venetian blind, it's some other shape. And it turns out that as the transit starts, that we call it ingress, and as the transit ends, egress, there is enough information in the high order terms of that light curve, that transit light curve, that could tell you whether something was round or not. And so Kepler, this fabulous spacecraft that launched in 2009 and has found now over 1,000 confirmed planets and 4,000 other candidate planets, has a lot of this information over the years since it launched. And there are scientists that are actually looking through the databases to see if they can see these higher order terms that might indicate something other than a round planet. And another really far out, but one of my favorite suggestions is this. There are variable stars in the sky called Cepheid variables. They are getting towards the end of their life. They expand and get brighter, and then they contract and get dimmer. And they expand and contract, and that period is very regular, and we understand the physics well enough to know exactly how bright a particular Cepheid will be based on the period of expansion. That makes these stars really, really useful to astronomers who are trying to figure out how far away things are in the universe. All right, so a Cepheid's really bright, and you see it over there, and you see it expand and get brighter and get dimmer and get brighter and get dimmer. You measure its period. That's easy. From that measured period, you know how intrinsically bright. So that's 150 watt, right, light bulb Cepheid, not a 60 watt. And you can say, well, but it appears dimmer than that. And you can figure out from how dim it appears and how absolutely bright you know it is, how far away it is. That allows us to measure distances across our galaxy, actually into the nearest clusters of galaxies. So this is a very critical part of our distance scale. A couple of very clever physicists said, well, if you're an advanced technology and you want to build a beacon that could be seen anywhere throughout the galaxy, what about Cepheids? Why not build a neutrino factory, orbit it around that Cepheid, and then the Cepheid expands and contracts, and it's thinking about expanding again And before it's ready to do so, you zap it with your neutrinos and you cause it to expand prematurely. So now you've actually created a short period as well as the regular, normal, long period. You've got a Morse code that can be seen throughout the galaxy. All you have to do is be able to build an orbiting neutrino factory. So because these are so important for distance measurements, we have centuries, at least a century and a half of data, particularly from the variable star amateur observers, and lots of data from Kepler. And so we're going through archives to look for this sort of thing, Morse code, a short period and a long period. And the thing about these almost natural signals is that you could imagine that we would find them in our normal astronomy. The thing about engineered signals is that they are something that you can't expect nature to produce. So in the radio, we look across a huge spectrum of radio frequencies and we look for power at just one channel on the radio dial. Nature can't do this. It's a kind of frequency compression that nature isn't capable of doing. So that's what our radio search is looking for, frequency compression. In the optical, we're looking for time compression. We're looking for the kind of signal that would be made by a laser, a bright pulse of light that lasts less than a nanosecond, less than a billionth of a second. Again, nature can't manage that. And if you found either of these obviously engineered signals, you'd have a pretty good case to make for somebody else's technology. And the reason for differentiating between the two is because you have to do different things to find the two different classes of signals. Almost natural you'll find by doing astronomy and astrophysics any way you possibly can, and encouraging your students and your postdocs to think about the anomalies they find in any large database. But for the obviously engineered signals, you have to build telescopes that probe parameter space that aren't being built by the astronomers because that's not where nature is able to produce signals. And so these kinds of signals require dedicated telescopes. Okay, now, I have to tell you that the cosmic haystack that we're trying to search for technosignatures is incredibly vast. It's at least 9-dimensional. There are 3 dimensions of space, 1 of time, 2 senses of polarization for an electromagnetic signal. You don't know what frequency. You don't know what kind of modulation scheme, if there's information encoded. And you don't know how sensitive you need to be because you don't know how strong the transmitter is or how far away it is. So you've got 9 parameters to probe. And all of the current SETI searchers are working on these artifacts, the frequency compression, the time compression. The uncertainty principle tells us that the time bandwidth product of any signal has to exceed unity. We've got technologies that get very close to that limiting curve. Nature's in a totally different part of the diagram. So as I've already said, we're looking for frequency compression, radio signals that are continuous wave or narrowband pulses, and time compression, broadband, very, very short optical pulses. So in the radio, we have this thing called the terrestrial microwave window. So I've got frequency plotted on the horizontal axis, a measure of temperature, which is essentially how much noise is coming from the sky, as the vertical axis. And you can see below 1 gigahertz, 1,000 megahertz, 1 billion hertz per second, there's a noise wall that rises. That's because there are a lot of free electrons in the interstellar medium, and there are magnetic fields in the Milky Way galaxy. And these electrons are spinning around those magnetic field lines, producing what we call synchrotron radiation. Anyway, it's a wall of noise that gets louder as you go to lower frequencies. Up there, we have an atmosphere on this planet, and we have water and oxygen in our atmosphere that emit more noise, and it gets noisier as you go to higher frequencies. In this region here, 1 to 10, there's the cosmic microwave background and not a lot else. So that's the quiet window that we have on the universe, and we are trying in our radio telescope work to build feeds and receivers that cover that whole window. That's what we want to explore systematically. So, here's a diagram. Frequency on the horizontal axis, time on the vertical axis. Don't have to explain anything more about the diagram than that. And I think you can see, obviously, there's noise and there's not noise. There are some signals there that are not noise. This is actually what the planet Mars looks like to us sometimes when both Mars Express and the Mars Reconnaissance Orbiter are on this side of the planet and transmitting data down to Earth. This is what an engineered signal might look like. And it works farther away than Mars. Okay, same diagram, frequency horizontal, time vertical. I don't know, can you see a signal there? Yeah, well, it's a little hard for the eye to see, but our algorithms find it with great ease. That's a almost 7 sigma detection in our system. So what we've done is devise algorithms that work on radio telescopes in real time, searching the frequency time domain, looking for these kinds of artifacts. And we're doing that every day at the Hack Creek Radio Observatory in Northern California, up near Mount Lassen, where we have the Allen Telescope Array with 42 dishes. Ultimately, if I get my wish, we'll have something like 350 dishes. Right now, we're working with 42. And we do what we call Sonata, SETI on the ATA. And since 2011, we have been using all of the exoplanet discoveries from the Kepler spacecraft and from the ground-based radial velocity and gravitational lensing studies to tell us the places on the sky where we know there are planets. And that's where we've been focusing our telescope. We actually do it 3 beams at a time with our interferometer, and we look at 3 different extrasolar planetary systems simultaneously to help us discriminate against our own technology, interference. If you're interested in following what we're doing, there's a website called setiquest.info. There's a whole tutorial about the site. You can figure out what we're doing, and you can take a look at our progress over time. So these are 2 dimensions on the sky. Declination is one, right ascension is another. This is an astronomer's view of the sky. You can see that big red blob over there. That's the 100 square degrees of the sky that the Kepler spacecraft has been staring at continuously. That's where those thousands of exoplanet systems have been found. The rest of the sky, those are exoplanet systems found by the radial velocity searches. And you can look at this daily if you're interested. If you actually want to amaze your friends and family at cocktail parties, and you have an iPhone, sorry, it doesn't work on Androids, there's an app called Distant Suns, right, which has the ability to poke on that little green radio telescope icon, and you can see the 3 directions that we're looking at that moment. And then you can check out the results the next day of what we saw. So one thing about having your own telescope that's dedicated to SETI is that you can follow up on interesting ideas, and you don't have to apply to a national facility and get on somebody's allocation timeline. So last month, there was a lot of fuss about one of these Kepler candidates called Kepler Input Catalog, KIC. 846, 28, 52. Now, I've told you, if you can see, the top curve is what's called a light curve. So that's the light from the star as a function of time running along the horizontal axis. And you can see, whoop, right, something's blocking the light from the star. And then again at a later time. Now, I've told you that Jupiter would block 1% of the light, and something like the Earth would block a part in 100,000. These drops are 20%. Something big is blocking the starlight. And so these were actually found not by the Kepler team and its automatic pipeline, but by citizen scientists who are looking at the Kepler light curves that are made public. And you can participate in that as well. And the reason the Kepler pipeline didn't find this, even though it's such a deep dip, is that it's not periodic. And so the citizen scientists found that. They began working with the Kepler scientists. They did a whole lot of additional study to try and understand what in the world this is. And nothing really works. The best model is that this particular star has a nearby companion star, and that nearby companion star may have disturbed a bunch of comets that are falling towards this 846, 28, 52, and those comets are being torn apart as they come closer to the star, and therefore that covers a lot of the sky, but there are all kinds of caveats because there's no infrared excess from this star, and yada, yada, yada. And then somebody says, well, if I were an advanced technology, I might build a swarm of solar collectors, sometimes called a Dyson sphere, to capture all the energy from my star and use it for whatever power needs my civilization has. So, something that might look like this. And of course, once that hit the news, that took off, right? So we said, okay, we got a telescope. And we spent a couple of weeks looking at this, and we can set some limits on the amount of transmitter power, anywhere between 1 and 10 gigahertz. They're not terribly tight limits. This is a few orders of magnitude stronger transmitters than we have on Earth. But they're interesting, and we'll keep doing that, and other people will eventually get time on larger telescopes and do it as well. So now I have to say what comes next for the Allen Telescope Array and for our SETI project is we're probably going to change direction. We've been focusing on all of these exoplanet systems that we've been told about because we know there are planets there. But we now make the statement that every star has a planet, more planets than stars in the galaxy. And therefore, we're going to start shifting to the closest stars because you can hear or detect the faintest signal from the closest stars. And so those stars, as I've already said, are primarily these small M dwarf, red dwarf stars. So we have a list of 75,000, and with our current instrumentation, we think that we can spend about 4 or 5 years looking at these nearby targets at a number of different frequencies, and we'll see what we find out. The Wolf 1061, B, C, and D were really good proof of concept that planets can form in the habitable zone of stars. So this is probably going to be our next approach. And because we have an interferometer, all of those little telescopes working together, we can not only look at individual directions in space, but we can make a radio image of a large field of view. So for us, one of the fields of view has 250 pixels. Right now we're using 3 of them. We pick out 3 and put them on extrasolar planets. But in fact, what we'd really like to do is use all 1,250 pixels at once, Well, we've got a lot of frequency to cover as well, and we're looking for very narrow band signals. So the standard correlator that's there, which has 1,000 spectral channels, 1,000 colors per pixel, isn't really what we want. We want to figure out how to put 100 million frequency channels on each of those pixels, and that's what we're working on. So that's life at the ATA. And that's not all the SETI that's going on. I have to acknowledge the work being done by my colleagues, particular at the Berkeley Center for SETI Research. They brought you SETI at Home over a decade ago. That's still going strong, looking at recorded data with your laptops and computers as a background screensaver. It's taking data from the largest telescope in the world, Arecibo, Puerto Rico, where they have a 7-beam focal plane array called ALPHA. They've also started recording data at the Green Bank Telescope, the world's largest fully steerable telescope. In Europe, there is a low-frequency array called LOFAR, spread across Europe and Holland. They're beginning to look for transient radio signals. An Italian group uses this 64-meter telescope in Medicina occasionally. The folks at JPL, who were part of the original NASA SETI program before it got terminated by Senator Bryan in 1993, have been out of the SETI game until they moved one of the telescopes outside of Goldstone, outside the fence, and then turned it into an educational facility called Goldstone Apple Valley Radio Telescope. And now they've begun a sky survey using students to scan the sky. So JPL is back in the game after all these years. And the Japanese are holding occasional campaigns where they get optical and radio telescopes to look at the same target simultaneously. And then we're doing optical SETI. Harvard is doing an optical SETI sky survey with a telescope that the students built themselves and instrumentation that the students built. The Berkeley group is using a 30-inch telescope at Leuschner as a targeted search, and they are reanalyzing all of the radial velocity data that's been taken at the Keck, the large Keck telescopes in Hawaii. We're also doing small optical programs at Campbelltown, just outside of Sydney. There's an Italian program called FOAM, and the most recent addition to the optical SETI programs is the Boquete Observatory in Panama. Again, all small telescopes, very easy programs that can be done by students or groups of individuals. And we are trying to move optical SETI down into the infrared because between the stars there is gas and dust that absorbs or scatters light. Because optical wavelengths are the same size as the dust grains, they are very affected by this scattering and absorption. But as you increase the wavelength into the infrared and the radio, the wavelengths get much bigger than the dust particles, and essentially the radio waves or infrared waves ignore the dust. And so we're trying to move our technologies into the near infrared. This is an interesting system that is on Mount Wilson, built by Charles Towns, an infrared interferometer. Charles has passed on. No one has taken up his research program. And so the Berkeley group is trying to put instrumentation on this to allow us to do SETI. And then this fabulous young professor, whose name is Shelley Wright, built her first optical SETI program detector when she was an undergraduate at UC Santa Cruz. She's now a professor at UC Santa Barbara and is building an infrared SETI detector system to be run on Lick Observatory outside, right up there, Mount Hamilton. Right? So, and then we're also looking at databases. So the WISE spacecraft has done a recent survey of the infrared sky. And on the lower left here, you see something called K2. It's an artist concept of what a Dyson sphere might be surrounding a star, a so-called Kardashev Type 2 civilization, a civilization that can manage to collect and use all of the energy from its star. And then over here, we go to a K3, obvious extension, although a bit mind-blowing, a civilization that can collect and use all the power from its galaxy. Okay? And so scientists have looked through the WISE database looking for K3 or K2 civilizations. There's a list of about 90 targets that don't look the way we expect a standard astrophysical target to look like. It's probably just astrophysics with a twist, but we're in fact going to take a look at each of those targets. And so the work that's being done today at Optical could detect our strongest laser transmitter, which is the petawatt lasers that are associated with the National Ignition Facility out at Livermore. It could detect those if they were up to 1,000 light years away. And the radio searches, again, could detect our strongest radio transmitter, which is a radar associated with the Large Radio Telescope in Puerto Rico. If it were up to 1,000 light years away and pointing towards us. So within 1,000 light years, there are about 1 million stars. And for us to have a chance of finding an extraterrestrial technology by looking at 1 million stars, it turns out you can do some math and make a lot of assumptions, but you're really basically saying that for us to succeed with just a sample of 1 million stars, civilizations, technological civilizations, are going to have to survive for about 100,000 years at least. So our future with SETI is to go to bigger instruments. The optical SETI we want to put on bigger pieces of glass. The 30-meter telescope that we're building in the US, the European extremely large telescope, 40 meters, as distinguished from OWL, the overwhelmingly large telescope, which was 100 meters. That's what they wanted at first and couldn't afford it. And then the Large Synoptic Sky Survey Telescope, which is under construction, which will make a movie of the sky and everything that changes on the sky every day or two. And for SETI, we're looking at, within the next 2 years, the Chinese will bring online something they call FAST. It's like a big Arecibo. It's built in a limestone karst sinkhole, but instead of being 300 meters across, it's 500 meters across. So China will soon be able to claim the largest radio telescope on the planet. And then farther in the future, an international project from which unfortunately the US has withdrawn, called the Square Kilometer Array, an array of thousands of small telescopes spread across the deserts of South Africa, the Kalahari Desert, and Western Australia. And if you remember the pictures I showed you of the Allen Telescope Array, you can see that we've actually had a large influence on the design of this next generation, maybe 2030 telescope. And I just wish we could get back into the picture as a country. Eventually, maybe something like this Colossus telescope that's being studied by astronomers in Hawaii, 70 meters across, working in the infrared, capable of detecting the background infrared heat from those kinds of Dyson spheres and other large solar collectors that might be built in orbit around exoplanets. So there's been a really good piece of news in the last year. Last July, Yuri Milner announced the Breakthrough Foundation Listen and Message projects. He's putting $100 million of his own funds into this search. He published an exquisite open letter at the time, making the argument that now was the time And this is the question that we should be investing in. And he's done that. These funds are going to Berkeley, and they will be renting time on large telescopes around the world and developing really good digital backends. So it's exciting. I want Yuri Milner's to be the first $100 million gift in a larger global effort to fund this kind of scientific exploration stably for the long future, because this may take a while to get done. And whether SETI ever succeeds or not is all about longevity. I made a quick sleight of hand, and I told you that if we're going to succeed with a million-star catalog of 1 million stars, that civilizations had to live to be at least 100,000 years old. This is a graphical representation of that. If technological civilizations pop up in the galaxy, but do themselves in or turn themselves off in short order, as we seem to have the potential for doing, right? Then SETI can't succeed. You will never get two technological civilizations close enough in space to be sensitive to one another and lined up in time in this 10 billion year history of the galaxy to detect one another. So for this reason, Philip Morrison, one of the first co-authors on the first paper of SETI in Nature in 1959, refers to SETI as the archaeology of the future. All right, archaeology, because if there's any information coming from that distant star, there's the finite speed of light, which will mean that we learn about their past. But the simple fact of a detection tells us that it is possible for us to have a long future. And this is the kind of change of perspective that I think is so important for the planet today. So Caleb Scharf, who's the chairman of the astrobiology department at Columbia, has this lovely quote from his book last year. On a finite world, a cosmic perspective isn't a luxury, it's a necessity. And so for me, the reason that I work on SETI, the reason I come and talk to groups such as yours, is to make this point that a cosmic perspective is something that we need to help ensure our long future. Because from the cosmic point of view, we are all the same. And that point of view helps to trivialize the differences between humans, among humans, that we're finding so difficult to deal with today. And I think that's the real benefit of SETI, is getting the planet to rethink itself and to see itself in a new perspective and work together to solve these challenges that we face that don't recognize national boundaries. So, thank you for joining me on my particular view of the 21st century.
Okay, we got about 12 minutes of Q&A. I'm just going to go around the room, put up your hands up to remind me.
So for that star that they saw, the large dip, how did they rule out that it was just a rock in our own solar system passing in front?
Because they're looking at a fixed point in the sky, and the rock in our own solar system would have differential velocity across the field of view. It wouldn't have given them these multiple aperiodic dips. They actually did look at that, and it's not something up close.
Isn't there a matrix of personal computers that might be put together around the world? I thought I heard that there was an organization that was doing that, trying to use the combined power of personal computers to increase what could be pulled from space.
There is, and that's called SETI at Home. It's been around for over a decade. It analyzes recorded data. At the moment, the data are recorded at Arecibo Observatory. And it's extraordinarily powerful. The only problem is it's recorded data, and what do you do when you find a signal? So the SETI at Home folks have some discretionary time from the director at Arecibo, and once a year, once every 18 months, they get their best candidates together and they go back and they reobserve. And to date, they haven't found anything. We've found in our work that there's a lot of benefit and a huge cost for doing the signal processing in real time, so that when you have the signal, you can follow up on it immediately. It helps to discriminate against our own technologies. And so when SETI at Home started, they first came to us and we said, no, we don't record our data, we process it in real time. But we gave them our algorithms. So they're doing the your screensaver on your laptop is doing the same kinds of searches for these frequency compression artifacts that we do in real time at the Allen Telescope Array. So yeah, SETI at Home was a great idea. I think it started the whole citizen science revolution. No, it's actually 12 years old, I believe.
Hello. Shouldn't we assume that life, advanced life in the universe is going to be machine-based life rather than organic life, that once you get to our level and then add another 100 years or so, that you're going to end up with a machine-based life form that is, living in space, around stars or maybe even between stars, and that we should be looking for that rather than organics?
Well, in terms of looking for technosignatures, I'm not sure there's a difference. And I'd actually probably rather have a machine running a transmitter continuously, because it won't fall asleep and it'll make sure that things get fixed. In terms of life, non-technological life, I think the biosignatures are the only game in town. And there are people who will argue that just as on our planet, microbial life is far more prevalent than complex life. I think we need to look for both. I think the biosignatures, right, as we march out in distance, and the technosignatures as perhaps a shortcut to finding either technologists or their machines. And we just hope that before the technologists became redundant, they programmed the machines to operate transmitters.
Good. Okay. There I'm on. Let me get my question back. There was an interview that Neil deGrasse Tyson did of Edward Snowden, and Snowden pointed out that it took mankind only about 60 or 70 years of radio broadcasting to realize that radio signals needed to be encrypted for privacy, so that it's indistinguishable from radio noise, unless you have the key, the code. And he points out that this might make it difficult to detect signals from intelligent life sources that are smarter than we are in cryptography. And so my question is, can you comment on that?
Yeah.
It may make it difficult to find really intelligent life.
Right. So there are a couple of parts to that question. Number one, I said to date, all of the SETI projects have been looking for these artifacts, but we are actually trying to figure out how to use improved computer capability to look for more complex signals. In particular, we're trying to figure out what kind of information-rich signals would transmit through the interstellar medium relatively undisturbed. And the medium may, in fact, give us some boundaries on the parameters. Now, it is true that an ideal, perfect informationally rich signal looks like noise. So if it's leakage, if it's encrypted signals they're using for their own behavior because they don't want somebody else at home. First of all, I've argued that it's going to be weak, and secondly, we probably won't find it. But if it's a deliberate signal, it maybe argues against encryption. Nevertheless, we are trying to get smarter. We always remain, we keep the right to get smarter in the future and try and do things that we couldn't do in the past. And computing is making that possible. So we're trying to approach that.
I really enjoyed your talk. As a lifelong amateur astronomer, you're just right up my alley.
Oh, thank you.
You mentioned that you're shifting your focus toward research on M stars, the closer red dwarfs. Will that will your measurement, get my question better. Will your detection methods be more focused on Doppler rather than spectral because of the dimness of the M stars, or will that matter?
Well, I'm not aware of any theory that said that if there's a technological civilization on a star in orbit around an M dwarf, that it will necessarily be fainter than a transmitted signal around from a planet around a G star. Total luminosity is less. Maybe if they're powering it by solar power, it might be less. We know so little, we're going to try the same thing, right? And any tricks and improvements that we can make. It's just going to be the target, the direction that we're looking is going to change.
I just wanted to ask about the general theory of looking for things. We have other sciences, social science and political science, that prove not to be science. And then I see this as a search that may be unending science quest, which is laudable, but I would just wonder if there's ever going to be a conclusion to it. Maybe not. Maybe that's what we're here on Earth to do, is keep searching for something. Thank you.
Well, I can imagine a positive conclusion. I can imagine us having success with the detection and finding number 2. And then immediately we will go look for number 3, 4, 5 and try and do demographics. Proving the negative doesn't happen, right? There are always some caveats. Well, we didn't look here, or we should look for. And all I can say is this will go on as long as people have the will to do it. When there's a threshold of pain that's reached and people are willing to make the astonishing, very important conclusion that we are, at least in all practicality, alone, then we'll stop. But that's a pretty momentous decision. Nobody made it through. Yeah.
How far away would anyone who was looking for us be able to see the strongest signal that we've made so far from? And how far away would the farthest thing that we could detect have come from, in how many 100 light years or whatever?
Yeah. If you take the power in our strongest transmitter at radio, which is the Arecibo planetary radar, that if somebody has our level of technology and Arecibo-like telescopes, they could detect that out to 1,000 light years. Of course, that signal only began transmitting in the 1960s. So it's the radio sphere that we've influenced from our earliest radio or television broadcast or leakage is 70 light years out, right? And if you want to get a response from them, it's half that distance. So we have no other metric to use except our own transmitters, but we have to say that we haven't been transmitting very long. and so are not ourselves visible very far away. So again, we're talking about the archaeology of the future. The signals coming from 1,000 light years away, if they're there, have been transmitted at least 1,000 years ago, and we're just now receiving them.
They're only dealing with things that are in our galaxy.
Well, you could be, I mean, the radio waves don't stop, they just get weaker. So when you're talking about things that are 1,000,000 times farther away, that takes a lot of power. And there are some strategies, and people have done this, where you get a galaxy, and you get a whole galaxy in your radio beam. So you're looking at 10 to the 11 or 10 to the 12 stars all at once. And you're saying, okay, there might be some distribution of transmitter powers out there. And somewhere on the tail of a distribution, there might be this incredibly powerful transmitter. And if you looked at all the stars in the galaxy at once, it might be strong enough for you to see it, even though that galaxy was farther away. So we've tried that. And we will do more of that kind of thing. But when you start talking about you have to put more power into the transmitter than currently falls on our planet, the insulation, that's a pretty big expenditure. Doesn't mean that it isn't being done. An advanced technology probably does have more access to a lot more power than we can manage today. So it's a strategy that's being tried.
Okay. Any other questions? I'm
One
sure.
more back there? Or you need to cut it off?
We do
We're
need to
late.
start wrapping up tonight. I'm sorry. Jill will be here to answer any more questions if you have any for a few minutes. So let's thank Jill for coming here tonight.